based on observations by other astronomers like Tycho Brahe and Galileo Galilei, Johannes Kepler came up with 3 laws about how planets move, and they are called Kepler's laws of planetary motion. The first law is called the law of ellipses, and it says that planets make elliptical orbits around the sun, with the sun as one focus of the ellipse. So the Earth does make an elliptical orbit around the sun, but it is very close to a perfect circle. And that is true of a variety of other planets as well. Some, like Uranus, are notably elliptical, but a lot of them, yes, they are technically an ellipse, but they look a lot like a circle. The second law says that a line that connects a planet to the sun will sweep out equal areas in equal times. This is called the law of areas, and it's a little easier if you can visualize it. So you have this line that connects a planet to the sun, and then you wait a month and you trace out that area. Later that year you do the same thing, and you end up with an equal area in equal times. That says that planets go faster when they're closer to the sun, and they go slower when they're farther away from the sun. And that isn't surprising if you know conservation of energy and conservation of angular momentum. However, in Kepler's credit, he did live 200 years before those ideas were solidified in physics. Part of the reason why we were able to discover conservation of energy and conservation of momentum was because of the observations of Tycho Brahe, Galileo Galilei, and others, as well as the law of areas from Johannes Kepler. Kepler's third law is not easy to say in words. It's a mathematical law. It says that the period of a planet's orbit squared is proportional to the length of its semi-major axis cubed. In other words, period squared is proportional to distance cubed. Ignoring the ellipse part and just calling it a circle, period squared is proportional to radius cubed. After Kepler had passed away, Isaac Newton was born, and he applied calculus to it and figured out what that proportionality is. And so Kepler's law looks like this. It's a really cool law, and since 1992, we have used it, as well as the Doppler shift, to find extrasolar planets. In 1992, I was in high school. It was a really big deal. It was the first time we ever discovered a planet outside of our own solar system. And we were able to do that by, this planet was huge and it was near a sun, and as it went around, the gravity caused the sun to wobble. Astronomers are great at naming things, so they call that stellar wobble. And that stellar wobble made the frequencies of the sun shift from red to blue to red to blue with the Doppler effect. And the period of that frequency was something we could measure very easily. Knowing the period, we could just plug it into Kepler's laws and find the radius, and then point our telescopes that far away from the star and wait for the planet to come into view. That's what we did, and it worked. We've done it hundreds and hundreds of times since, and have discovered that extrasolar planets are extremely common. We used to think they were maybe pretty rare, and we were very wrong. Extrasolar planets are really, really common. So those are Kepler's 3 laws, and they are things that you do need to have memorized. AP, you might have to derive Kepler's third law, and so let's go ahead and do that.
We know gravity is providing a centripetal force, so let's set those equal. Plug in mv squared over r and gm1 m2 over r squared. Cancel some stuff. Realize that speed is distance over time. That's circumference over time. That's 2 pi r over period. Plug that in. Multiply both sides by period squared, rearrange, and we are done.
Here's another gravity detail for you. Escape velocity. When we first started talking about space travel, we were like, hey, what if we just load something into a cannon and launch it off the planet? How fast would it have to go? That's actually not that hard to calculate, so let's do that.
So instead of using a rocket to get off the Earth, what if we used a cannon? What would our initial velocity have to be? To find out, let's use the work energy theorem. It starts with some kinetic energy and some negative potential energy due to gravity, and very far away, it's barely not moving, and it's too far away to have any potential energy left. Kinetic energy is 1/2 mv squared, and gravitational potential energy on this scale can't be mgh, it's minus gmm over r. That's force times distance. Why that works so well with a force that decreases with the square of the radius is something that requires calculus and is outside the bounds of this course, so you'll just have to trust me. This is a straightforward equation to solve, and we get escape velocity is equal to the square root of 2gm over r. That's a little over 11 kilometers per second, which is really, really fast. We'd best stick to rockets.
So, launching things off of the planet directly is really very impractical, which is why we use rockets. We could use instead maybe a giant rock that we've tied a huge cable to that we can winch things up and down like a space elevator. Sounds like a crazy idea, but it might actually work if we can invent a material that's strong enough. There's another even crazier idea called a Skyhook, which Kurzgesagt has an excellent video on. I'll link it in the comments down below if you're interested. So, escape velocity also has some real meaning for astronomy and how planets evolve. We know that Mars doesn't have much of an atmosphere, right? And the reason why for that is because Mars is a smaller planet. It's got like a third the amount of gravity that Earth does, which means the escape velocity is a lot lower. That means that the bouncing around molecules of atmosphere that are sometimes shot up in the air are much more likely to escape the planet and just boil off into space. That happens on Earth. It happens with any helium we release. It eventually bubbles up to the top of the atmosphere, and it's so light, it gets enough speed, it just takes off, and we never see it again. That happened to Mars's atmosphere over a long period of time, and this is why you have situations like Venus is a crazy hot planet. It's got clouds of sulfuric acid, and it's covered in carbon dioxide with a runaway greenhouse effect. So it's like 900 degrees Celsius on the surface. All of the lighter molecules boiled off as the planet got too hot. They reached escape velocity and got shot off of the planet, like literally shot out into space, leaving behind only the heavier, denser stuff that also happened to make things hotter and turn into this runaway effect. Something else we can apply circular motion and gravity to is satellites. If you have a satellite dish at your house and you want to point it up at a satellite, that satellite needs to be in the same spot, right? So as the Earth rotates, the satellite has to stay above the same spot. You don't want to have your satellite dish tracking across the sky to find this satellite or that satellite. And so you want it in what we call geostationary or geosynchronous orbit. So that means it goes around once every 24 hours. And interestingly, we're kind of running out of space because there's only one radius that gives us geosynchronous orbit.
Looking at Kepler's third law, the period we're looking for is 1 day, 24 hours. We can't change the number 4, we can't change pi, we can't change g, we can't change the mass of the planet, which means there is really only one radius. You can calculate it if you want to. But the point being, we have this shell of space where we want to put almost all of our satellites, and that shell is filling up with a dangerous amount of space junk. It's a very interesting problem and one we're going to have to do something about in coming years. See you next time.